Assalamu alaikum. Let us continue with our discussion of random variables. And today I will remind you of this example which I used to motivate discussion of random variables. If you remember, on the left you have one partitioning of the sample space. Which sample space? Where you have two dice, you throw them, and you want to see which how many dots show up on each. So on the left you are interested in all the details, so you want to look at each die to see how many dots it shows up. So if you have white die and a red die, for example, this, what would this correspond to? This would correspond to 3 dots on white die and 3 dots on red die. This would correspond to 6 dots on white die and 2 dots on red die. But there is too much detail, and just remember, mathematically you can combine the sample space of one die with the sample space of the other die, just cross it, Cartesian product, and you have this combined sample space. What if we are interested not in the pair but in the total number of dots? Let's say that's all I need. Total number of dots facing up on both dies. So what will I do then? I will partition this sample space of 36 elements in such a way that in each subset all the outcomes correspond to the same total number of dots. So let's see an example. Let's say I am focusing on this one, this event. What is common in all these 3 elements? They all have the same total number of dots. How? For example, if I start with this one, how many dots do I have on the white die? 3. How many dots do I have on the red die? 1. So what is 3 plus 1? 4. This one, 2 plus 2, 4. This one, 1 plus 3, 4. See? So you can take any of these. Let's say if I look at the last one, this one, 6 dots on white, 6 dots on red, 6 plus 6 is 12, and there is only one element of that. So that's how we use the idea of partitioning to isolate events of our interest. Now let us mathematize all this discussion. So if I use the label K for the total number of dots facing up on both dice, so AK will be A. You see, you cannot have A1, because the minimum total will be 1 plus 1 is equal to 2. So it has to start with 2 and cannot exceed 12 either. So 2 up to 12. So A2, A3, and so on, A12. So AK will have pairs of this form. If you look at this, K doesn't change because K is there. So I and K minus I think you have also seen this in convolution. So if you add I with K minus I, what do you get? The answer is K. So which means that I is allowed to take any value from 1 up to 6. But K will not change, So when you add this, and this is exactly what is happening. If I go, for example, if I pick this one, in all these elements, this will be my A5, 4 plus 1, 3 plus 2, you see. So the pairs change, but the sum doesn't change. And the probabilities of these events of interest is simply the size of the event divided by the size of the sample space. And if you look at this, this may sound complicated, but it's very easy. For example, if I start with the first one, it has only one element, so 1 over 36. Second is 2 over 36, then it is 3 over 36, and so on. Now this probability increases up to 7 when the sum is 7. So you can verify that is k minus 1 over 36. So the probability increases from this side. As you move on, the probability increases. And the probability also increases from that side. Yeah? Because here you have smallest probability, there you have smallest probability. They both increase and they must reach maximum somewhere in the middle. And that is why, that is what you see here. For total from 2 to 7, this is increasing the probability. And for the other values, it is decreasing. 13 minus k means that it is decreasing. And now we can move on with the rest of our definitions. So if I want to define a random variable, the random variable must assign how many values? Not 12, but 11. Yeah? Because it doesn't start from 1. If it has started from 1, you would have 12 values. It starts from 2, so you have 11 values. 11 different values, and the labels. Remember here, we are using the same notation which we did before. The only difference from the previous case is that k started from 1. Here k started from 2. Now the probability measure induced by x takes the same form. You see, there is nothing new here. Yeah. So you have that same, because we have these probabilities. That's the key. We have the probabilities of our events of interest. Those same probabilities will be used to weight these Dirac measures, and my probability measure for x will simply be a weighted sum of the Dirac measures. Now the distribution, the probability distribution can be easily written down now. The support set is, of course, elements from 2 up to 12. This strictly defined PDF is simply, at each k you have those pk's. So you see there is nothing fancy. And for the distribution, you just add all the previous values, starting from 2, remember. If you want to write the PDF and the CDF, you can use the clipping functions. So that is not so difficult. I just wanted to show you that you can apply this theory to any problem. Now, because I already told you that this probability increases from 2 up to 7 and it decreases from 8 up to 12. Yeah, you can see this minus sign. There k is plus, here k is minus. So it's a falling line, that's a rising line, and that is exactly what you see in this histogram. This is the exact histogram which I showed you in the first lecture, and you see it increases from 2 to 7 and it decreases onwards. Now this example motivates a more general formulation of discrete random variables, because now you cannot be sure which values will be taken. Of course, you are still talking about discrete random variable, but the number of the type of values can change. So in a general setting, we will simply start. I mean, I would like you to read all this yourself because this is pretty much standard. I start with a sample space, actually with an experiment. Then I start with the event space based on my interest, partitioning. Yeah. Then and pictorially you can see it this way. The sample space is partitioned into several events, and remember, in some cases these events can even be infinite depending on the problem at hand. So the random variable definable in such a scenario must assign as many values as there are um, partitioning events. So you see, x1 is assigned to all elements of a1, x2 is assigned to all elements of a2, and so on, and the rest is actually standard Dirac measures, weighted sum, and so on. So I think that is also for you. Let's move on. This is a second example I added, the bit transmission example. And again, this is not new. We covered it many times in the context of total probability, conditional probability, and so on. The reason I included it here is to appreciate the simplicity in language when you bring in random variables. So when we were dealing with this same problem in sets, it was not very easy because we didn't know how to write the sample space. But now the bit transmitted can either be 1 or 0. So you can say that the input bit is a random variable and it's a Bernoulli random variable. And the output, imagine you have all the logic which converts all the analog waveforms to digital waveforms. The output bit will also be either a 0 or 1 once it is finalized. So that is also a Bernoulli random variable. And these are the transmission channels. So this epsilon, yeah, and these 1 minus epsilon, these are the transition probabilities. So if you send a 0 and it is received as a 1, that is the probability of that type of error is epsilon, and same for the other type. When you send a 1 and it is received as 0, and if it is not received without any error, that is 1 minus epsilon, and so on. Now let's formulate a problem just to see whether you understand what we did so far or not. So let's say, I can expect to have enough data to understand this part x. So let's say the input random variable, which is the bit I am sending, let's say that is Bernoulli distributed with parameter 1 minus p. Now what does that 1 minus p mean? 1 minus p means that 1 minus p is the success, the probability of success. So p will be the probability of failure. So it means that x is equal to 1, x is equal to 1 will have probability of 1 minus p, x is equal to 0 will have probability of p. Now, I would like to use this information combined with these conditional probabilities to work out the distribution of y. Of course, you can say, okay, it is also a Bernoulli random variable, but what will be its probability of success? It will not be that same thing because these are different variables. Channel will change all the distribution. So let's gather the conditional probabilities, and you see how easy it is to write these events. You see, you don't even need to write A, B, C. You just write the variable and the value. So let us start with this one. The probability that you send a 0 and it is received as a 1. Yeah. So that is which? That is this path from 0 to 1. That is epsilon. It is written there. Yeah. It is written there. The probability that you send a 1 and it is received as a 0. You see, you send a 1 it is received as 0, it is also that. And same goes for the probability of no error. So you send a 1, it is received as a 1. You send a 0, it is received as a 0, 1 minus epsilon. So I have, remember, I have two pieces of information. Information of the input bit, which is Bernoulli random variable with the parameter 1 minus p, and the conditional probabilities of which model the channel. Now I need to construct the probability distribution of the output bit or the received bit. So because I only have two possible values, I don't need to go into too much math, and I just use the law of total probability for the y is equal to 1 and for y is equal to 0. So received bit is 1, received bit is 0. I just take into account all the possibilities. So a 1 can be received either because a 0 was sent and there was an error, is one possibility, or a 1 was sent and there was no error. So if you plug all these values, you get this probability. And same goes for 0. 0 can be received either because a 0 was sent without error, or a 1 was sent and there was an error, so that it became 0. So here you go. Now you have everything you needed, and because there are no other values, the probability of y taking any other value will be 0. So now we know it is Bernoulli, and we know the success, and we know the probability of success is this one. Now instead of writing that whole horrible expression every time, let's call it theta. So let's say this one is theta, or you can come up with any name. So my y now is Bernoulli distributed with that theta, and theta is that expression, and we are done with it. Just to make sure that how will you use these probabilities to answer important questions. So how will you represent the bit error in this scenario? You see, we spoke of Borel sets all the time. Borel set in this problem is very complicated because you have two random variables, x and y. Yeah. So when you say error will involve both at x and y. Yeah. So you send a bit and something else is received. You send this bit and something else is received. So if I use pair, so of course the Borel set will be in 2D, not in 1D, because of two random variables. Let's say the first one is a value of x and the second one is a value of y. So this would mean that my Borel set in 2D has two pairs, 0 sent, 1 received, 1 sent, 0 received. Of course, if I need to assign probabilities to this Borel set, I need to take this, I need to invert it. So I need to work out the pre-image. The pre-image, let's call it A. Remember, I cannot say x inverse, y inverse, because it's a combination. Both x and y are responsible for this set B. So I cannot say x inverse of B or y inverse of B. But I know what I'm doing. I know where will this pair come from. So 0 sent, 1 received. Look carefully. 0 sent, yeah, 1 received. Y is equal to 1. X is equal to 0. 1 sent, 0 received. And just take the union. So if you want to find the bit error probability, regardless of which bit was sent, you just add these two, and that turns out to be epsilon. So yes, we are done. I think these were enough examples. Finally, I can start with the topic which we actually started once, but we could not continue with it, and that is the typical value of a distribution. You have already seen examples of distributions which are symmetrical, yeah, and which have a single peak. Yeah. So let me show you an example before I move on to the math. We already have an example like this. This is a distribution with a single peak, yeah, and which is symmetrical. So there is as much data to the left of the peak as is to the right of the peak. So distribution symmetrical about a single peak. In this case, everybody will agree that this value which maximizes the distribution, you also call it the maximal value or extreme value, that is the typical value, yeah, the most likely value. We also call it mode. So this will be mode. Okay. But we cannot guarantee that each time we will have a distribution that is symmetrical. So if it is not symmetrical, maybe, let's say I show you some very strange distribution. This is x, and on the y-axis you have PDF, and let's say the distribution is something like that. Now this is the mode. So it is debatable to call it a typical value because there is more area to the left than to the right. So you would expect the typical value somewhere here to have a balance. And that is what leads us to the concept of mean. You will see it. Another candidate for the typical value is median. So median is just sorting all the values from left to right and locating a value at which the CDF is 50%. Let me just read that out. So median is the value at which the CDF is equal to half. Now how do you picture this? Let's say I have, sorry, it was a horrible drawing. Let's say this is x-axis, this is y-axis, and this is the CDF, and these are values of x. And let's say CDF starts as 0 and it somehow ultimately reaches 1, and let's say this is the point. Oh, this is horrible. I think something went wrong, so I just paused it for a while. So we get back to this CDF. Let's say this is the value at which, let's call it M. This is the value at which the CDF reaches 50% value. So you can clearly say that this can be called a middle value. Actually, there are situations where you will have 2 or 3 values or a range of values. So it can be seen as a generalization of the middle value. Middle value sometimes cannot be decided, so you will have a band of middle values. Anyway, we are not interested in middle value, we are not interested in mode. This topic is about the mean, which is also called the expectation. So now, what is the main concept of mean? If you remember, we have seen this data a few times. So let's say this is just the index of trials, first trial, second trial, 10th trial. So let's say you have 100 data points, and at each 100 runs of some experiment, and uh, and at each point you have different values. Yeah, so x takes these values. So you see it's pretty random. So what we mean by the mean value is a single value. You see this dashed blue line? It is a single value which has the least squared distance from all the other values. So you can say it is the best fit of a horizontal line. Horizontal line means that we want a single typical value. This one. Now, why do I say that it is the best fit? We need a criteria. So if I use, so let's call this mu, yeah, and let's say I want to estimate this mean mu from this data. So let's use a hat for that. Yeah. Hat means that I want to estimate the true value of mean from data, and this subscript n means that I'm using n data points. So if I use the squared Euclidean distance as a measure of misfit, what can I do then? I just take each value. So I take all the values which the variable can take, and I take the deviation of any value, yeah, one of these values, from the so-called candidate for typical value, because I claim that this is the typical value and this is best fit. So the square distance of each point, and then if I add all those square distances, I should get a measure of fitness. Now, why do I say it's a measure of fitness? Because if this sum of all distances is small, I can say it is a good fit. If it is large, I will say, okay, the fit is not good. Now, what is this a n of k doing here? This is required because I am taking not the actual values, but I am taking the possible values of the sample space. Not the sample space, the support, to be very honest, because these are real numbers on the real line. So this value will appear multiple times because the number is very large. This n is very large. So an is the absolute frequency observed in those n trials. So each squared distance from the typical value, which is unknown, to each data point is multiplied by the frequency with which that value is observed. So for example, if a value has been observed 10 times, this squared distance will appear 10 times. So because you want to sum all distances, you have to multiply that 10 times and so on. So now I want to find this unknown value which will minimize this squared distance, sum of squared distance. Now if I use calculus, I just differentiate this. So I view this as a function of the unknown, and I differentiate this and set it to 0 to find the maximum. No, the minimum, sorry. minimize. So if I apply that summation power rule set to 0, and if I just move on at the end, I will have an expression for this unknown, which is, you can see, the sum of all values. You see each value multiplied by frequency. So it's essentially is the sum of all values, not all possible values, but all observed values, because possible values, each possible value is multiplied by the frequency. So it is the sum of all observed values divided by the number of trials. So it is essentially it is the arithmetic mean. And if I recall that the absolute frequency divided by the number of data points gives me the relative frequency, relative frequency. So I can also express this estimated mean by a weighted sum of all values, and each value is weighted by the relative frequency. Now I also know that if I take this n to be very large, these relative frequency will approach probabilities, and I can now have a definition for the mean. Mean is simply the weighted average, each possible value weighted by the probability associated with that point. So remember, it is not enough to say that I have to take the arithmetic mean, because arithmetic mean can have many different contexts. This is called expectation or mean value of the random variable, and this has a specific interpretation. It is the best fit in the context of long run observations. N has to be really large for this to be a probability, otherwise it was relative frequencies. So just saying it is the arithmetic mean is actually ignoring all this important information. Now we established this for discrete random variable, and that's why you have this sum, but this concept can be applied to continuous random variables as well. Then you simply will have this summation replaced by integration. So in a more general setting, the mean value of a random variable x which we, on one side we can denote this by mu, because we already have mu subscript x, means that we are talking about the mean value of x, and it's also seen as an operator e, the expectation operator applied to the random variable x. Remember, you have an operator acting on x. X is a random variable. It is a function. So when something acts on a function and returns a single number, this is actually acting on all of the random variable, all its values. Yeah. So you should not see this as multiplication or something like that. So it looks very similar to a Laplace operator. So I come back to this later. This is simply a repetition of that. Yeah. Weighted average, hash for the discrete part of the random variable. And if it has some continuous character, it will also have another sum. Yeah, a weighted sum. And remember, each value is weighted by, not by density, but by probability, because density multiplied by dx is probability. And both these, this sum and this integral can be written in this single integral, the modern integral, which you integrate x with respect to a measure. Remember, we have seen counting measure, we have seen Lebesgue measure, the length area thing. Here, this is the probability measure. So we are integrating possible values or the function x representing the possible values with respect to the probability measure. Yeah, and remember this Bx was that Borel set, differential Borel set. So you take tiny regions on the real line representing Borel sets and you take the integral. Now the reason I want to write this is it is much more convenient to write this integral because we know it will become this summation for discrete, it will become this integration for continuous, and for mixed you will have both. So this is a more universal definition which includes those as special cases. So let's take a few cases because we did this last time as well. For the first few examples, because now we are dealing with discrete random variables, so it is better to keep this definition in mind, where you just take the weighted sum of all possible values, and weighting is done by probability. So let's start with the Dirac distribution. It has a deterministic constant value a, and because it's a constant value, the expectation, this weighted sum will have just one value. Yeah, that's the only value with non-zero probability. Actually, the probability is 1. All the other values have 0 probability. So when you take the weighted sum, that same a appears in your answer. So it's just another way of saying that when you are speaking of a deterministic constant, the expectation is the same constant because there is no randomness, there is no uncertainty. For the Bernoulli random variable, x distributed according to Bernoulli distribution with probability p of success, what is the mean? You again take the weighted distribution. So you have two values, 0, 1. 0 will be weighted by 1 minus p, 1 will be weighted by p, multiply, add, and you get p. So that probability of success, now you have seen a new interpretation. The probability of success is not only a probability, it also happens to be the mean value of your Bernoulli random variable. Now this is interesting because in lecture 2, I also posted this as a question on Facebook group. If you remember, the relative frequency in the long run was also viewed as the average occurrence per trial. And we know Bernoulli random variable is an indicator function. So that occurrence, if you go back to lecture 2, there we had used a symbol B N K. I don't know if it was BNK or something. It was not BNK, it was BN, I think. So you can link this probability P to that relative frequency. It is relative frequency and it also is the average value of your Bernoulli random variable. Now let's move on with the next example. Discrete uniform distribution. Yeah, discrete uniform, n possible values, all with same probability. Weighted average, add all the values from 1 to n, and each having the same probability, so 1 over n. So weighting is uniform, and if you take the sum of these, actually you take the sum of first n integers, divide by n, and you know this. It makes sense, yeah? The first integer, the last integer, add the two, divide by 2. And because it's uniform, you can do that, yeah? If something is increasing uniformly, you just take the first value, the last value, divide by 2. Now this is not possible if it was going like that or like that. This would not be that simple. Now let's complicate things a little bit, because you will not have these simple examples all the time. We will also have complicated examples. So before I move on to this, let's go back and see the example which you just saw. This one, yeah, the two dice, throw of two dice, and we see that the distribution has a peak here, and it is symmetrical, so we would expect our mean value to be very close to 7, yeah, because that is the mode, and we also expect this to be the mean. So remember, we have the pKs and we have the values. So these 11 values, each one will be multiplied by the respective probability, and then we add all these products and we get the mean value of that random variable. You see, in fact, this is also the same data, yeah. That 7 is here, that 7 between 6 and 8 is the mean value, and that 7 is also the mean value here. Now we need to show that we get the same answer by the mathematical formula for the mean. So the mean value of x, so now we are working out this two dice experiment, and I want to know the mean value of x. And what was x? The number of dots facing up on both dice. So I take all these 11 values, I weight each one by the respective probability, for which I already know the expression, and I know that pk had two expressions. One was for values 2 up to 7, it was this expression, you see the increasing expression, and for the rest of the values it was a decreasing expression, 13 minus k, and these probabilities multiply my values, possible values. Now if I simplify this, I can simplify part of it. So let's get rid of this denominator 36, just take it out, and this is from 2 to 7, and k times k minus 1, k times k minus 1, 2 to 7. Here I want to do something. I want to see this same k times k minus 1 there as well. And how can I do that? If I break down this 13, yeah, into 12 plus 1, so that plus 1 will be combined with minus k, so 1 minus k. If I take the minus sign out, I will get k minus 1 multiplied by k, that 1 over 36 is out. You see, now I have two terms. One term, k times k minus 1, summation applied, and another term, k times k minus 1, summation applied. This summation is from 2 to 7, that summation is from 8 to 12, and that is with a minus sign. Now what do we do with that 12? Yeah, that 12 is multiplying this k, and that 12 has to be divided by 36. So that's why we still have that 36 here, and that 12 has to multiply this k, and the summation is not going anywhere, so you still have the summation. So we have basically three sums. Forget about this now, okay? Forget about this. I think I should have simplified this. Yeah, I think I forgot to remove that So we can deal with this one. But you need to understand something, that for you it is possible, it is very easy to deal with this kind of summation, yeah, where you just have a sum of integers. It is not very straightforward because it is not going from 1, it starts from 8. It is actually an arithmetic sequence, series. But this is very different, yeah. You have a falling factorial. Remember, it's k minus 1. You have this falling factorial with two factors. And I mean, it's not very straightforward to deal with these sums. Of course, you can find formulas on the internet, but you don't get inspired by those formulas. They just they don't show the logic behind. So let us stop here and introduce something which will help us deal with these difficult summations, and that is called the forward difference operator. It is very simple, similar to a derivative. A derivative is also an operator. It's called the differentiation operator. And now we are dealing with the difference operator because we are dealing with discrete quantities. So what is a forward difference operator? Let's use delta for it. And we will apply delta to any sequence sk. Remember, sk means S for sequence and k is the index. Just like you write in signal system, x of k. So you in signal system you would have written this like that. So you have a discrete time sequence. Here we use k as a subscript. So what do we mean by this difference operator? I just take the difference. Yeah, I subtract this present value sk, the actual value, from the shifted value, and this is the forward shift. So essentially it is a shift operator going forward, not going backward. That's why it's called forward difference operator. Now let us apply this delta operator, this forward difference operator, to the types of polynomials we see in this expectation. So let's apply it to something like this, the following factorial. And because the highest power here is k squared, so I will call it the quadratic falling factorial. Quadratic falling factorial. K falling factorial 2 means that I just have two factors, k times 1, k minus 1, k times k minus 1. And I'm applying this finite difference operator. So what will happen? I will subtract this k times k minus 1 from the shifted version. What happens? K becomes k plus 1, the shifted version, and k minus 1 becomes k. I simplify this and I get 2 times k. Now what can I learn from this? What I can learn from this is this. Remember, just like integration will undo differentiation, so by the same logic, summation will undo this difference operator. Yeah. So difference operator and summation are opposite to each other. Derivative and integral are opposite to each other. Now, this difference operator, if I apply a summation on top of it, these two must cancel and I must be left with the original thing. That's pretty standard. So let's see some pattern here. I know twice k from that formula. Twice k is delta applied to that quadratic falling factorial. So if I now want to see, although I know the answer, but I just want to check this method. Summation from 1 to n applied to k. Now this k I know is a result of some differencing operator except for that 2. So if I multiply this by 2, yeah, and divide this by 2, I will have that half. That 2 will go inside 2k, and I can express that 2k as a difference operator applied to the quadratic. The difference operator and the summation operator, they have to cancel, and I must be left with only the thing on which that difference operator was applied. So you apply delta and then you apply summation and you are done. But because this is a definite summation, just like definite integral, remember? When you take the definite integral between two limits, at the end, when you apply the antiderivative, you take the difference of values at b and values at a. We will have to do similar thing here. Even if this delta and this sum cancel out, we have to find a final difference. Yeah, so this will correspond to that limit, and this will correspond to this limit. You just work it out. Just notice that you must be wondering why we have n plus 1 and not n, because it's a forward operator. Yeah, so this delta, the last value of that delta will be left, the upper last value, and the lower last value will also be left. So the upper last value, because we apply this forward operator, that n will become n plus 1, and this will not change the last one, because you cannot go backward. Yeah? So 1 applied following factorial 2, n plus 1 following factorial. If you don't follow this, let me give you another way of looking at it. If I replace this with these expressions, I can see another pattern. I have this sum of differences. So this minus that, that minus that, that minus that, all these intermediate plus minus. You see, here it's minus, and the next one this will be plus, and a lower value will be minus. All these intermediate values will cancel out, and you will just be left with the largest value on one side, the smallest value on another side, and that's it. You get your sum. You get the same sum basically. If I apply the same delta operator to a cubic falling factorial, which means that I, instead of two factors, now I again start with k, but k times k minus 1 and then k minus 2. So I have three factors. That's why k subscript 3. Apply this difference operator, the original sequence from the, subtract that from the shifted sequence. Remember, k becomes k plus 1, k minus 1 becomes k minus 2 becomes k minus 1. Simplify and you get that expression. Now let's see what happens. What you discovered is that 3 times that falling factorial, the quadratic falling factorial, yeah, just like this one, 3 times of it is simply the delta of the cubic falling factorial. So if I want this summation, a summation of quadratic falling factorials, I have to recognize that this only except for 3. So if I multiply by 3, If I divide by 3, this 3 goes inside, that 1/3 remains outside, and I can see this as a result of the difference operator. Now on top of that, I'm again applying the summation. Summation will cancel out with the differencing operator, and I will again be left with those two limits, the upper one, the lower one. And yes, I have my answer. Yeah, this is that permutation. So I only need these two results. This one, which is not new for you, I just wanted to motivate this discussion. And this is actually a follow-up of that. You apply these two results to these sums. Forget about this one because I will remove this. I just apply this to this one, to this one, to this one. Now how? Remember, some of the summations are from 2 to 7, from the small number, some of them are from large numbers. So let's work these out. If I go from 1 to 12, I can simply apply this formula. Done. If I go from 1 to 7, the same formula with different settings. 1. But if I want a sum from 8 to 12, not from 1 to 12, nor from 1 to 7, I can simply subtract this one from that one. Why? If I start from 1 to 12 and then I subtract from that a sum from 1 to 7, 1 to 7 will disappear and you will only be left with 8 to 12. So I just subtract this 28 from that 78 and I am done. Same goes with this. The sum of those following factorials from 2 to 12 is this. From 2 to 7 is this. Subtract these two, you get from 8 to 12. Yeah. You must also be wondering why this summation is from 2 and not from 1, because if you put 1 there, k minus 1 will be 0, so you are adding 0. That will not change anything. And if you plug these values in your expressions, oh, you got that exact 7, which we expected. Remember, this 7 from data, time series data, and that 7 from the histogram. So this adds some confidence that what we are doing makes sense. The next topic, I will not start this now, but just prepare you for that. That you remember we dealt with transformations. Yeah, we deal with a standard random variable and we apply some transformation, a point function, to derive another random variable. Naturally, we would like to have a formula for the expectation of a transformed random variable. So this will be the topic of our next lecture. Okay. Bye for now. Thank you.